In the first century BC, Roman orator Cicero traveled to the island of Syracuse to find the grave of a very important man. No one knew where this grave was, and he navigated to a graveyard with all the gravestones surrounded by overgrown weeds, until he found one gravestone of someone he knew right away. The gravestone had this design on it. This is a diagram of a sphere contained within a cylinder, encased within a cylinder. He knew right away that this was Archimedes. Archimedes was famous in Greek antiquity for many things related to science, math, engineering, and he picked this design to be his gravestone, famously. Tonight, I'll share with you why this is the case. In his day, Archimedes was famous for discovering the laws of buoyancy, which relates to the force water pushes up on an object once it's submerged. He had a very intuitive understanding of simple machines, such as screws, levers, and inclined planes. He once famously said, "Give me a lever long enough and a place to stand, and I can move the earth." He was also infamous for designing a death ray of sorts to defend the island of Syracuse against raiding Romans, essentially creating a concave mirror that reflected the rays of the sun and could burn invaders. But of all of these accomplishments, the way he really wanted to be remembered was this. Tonight I'll share with you three famous geometry ideas that Archimedes discovered in his time and why they're important to be celebrated. First is the area of a circle. Second is the surface area of a sphere. And the third is the volume of a sphere. Pi r squared. I don't even need to tell you what that, sorry. I don't need to tell you what that is a formula for. You already know it's the area of a circle. Now, when I was younger in school, I learned the formula for the area of a circle, circumference of a circle, we all did, but I didn't know where it came from. It actually came from Archimedes. The shapes that are easiest to calculate areas for are things like rectangles, because you can align them in grids and calculate the area of a rectangle by finding the length of the base, length of the height, and multiplying them. Similarly, you can do the same exercise for a parallelogram. And you can also do this exercise for a triangle. Triangle is half of a parallelogram. Problem with the area of a circle is that before Archimedes, no one actually knew the area of a circle, how to calculate it. Why? Because these three shapes have something in common. They all have straight sides. Circle is different because circles are round. So what Archimedes did was he compared a circle to shapes with straight sides. But before we dive into the area of a circle, we should talk about what is pi. So imagine a circle, and what I'm going to do here is label the circumference of the circle, which is the length all the way around the circle, as c, and the diameter of the circle, which is the width of the circle, as d. Now, if we scale the circle by a factor of 2, if we find a circle that's twice as big, the circumference of the circle is twice as big, and so is the diameter. Now, if we take that circle, make it even twice as big as that, you'll have a larger circle with a circumference of 4 times c and a diameter of 4 times d. Now, all these circles These are basically the same shape, but they're all scaled. So what stays the same across all of these circles? Well, if you take the ratio of the circumference to the diameter of all three of these, you get something that's the same. No matter if you how much you scale up the size of a circle, the ratio of the circumference to the diameter is going to be the same always. What is that number? Well, that's what pi is. The ancient Greeks defined pi to be the ratio of the circumference to the diameter of a circle. So what is pi really? How do you calculate it? Because I didn't give a number here. Well, clearly pi is 3.1415192653589673264333, give or take. The ancient Greeks had no way of calculating that with such precision. Archimedes made an attempt. What he did was he took a circle, he encased within the circle a shape with the same number of sides or sides of the same length, and he encased the circle within another shape, another square with the same shape, just scaled up. And what he did was he calculated the perimeters of these two squares and divided them by the diameter of the circle. And what he got was what you would get in this situation is pi is a number between 2.8 and 4. That's not quite 3.14159, but it's better than nothing. You know that the number is right around 3. He did the same calculation with hexagons. And when you do that, one thing you'll notice is that the hexagons hug the arc of the circle a lot more closely than the square did. And when you do that, you get a number for pi that's between 3 and 3.5. Archimedes took that another step even further. He calculated a shape, the perimeter of a shape that was 96 sides, and he got roughly 3 decimal places. It wasn't until special math from the 18th, 19th, and 20th centuries that we were able to calculate pi to 50 or 100 digits. But for all practical purposes, getting 3 digits is pretty darn good. And the method Archimedes used to do this was to take the circle and encase it in shapes with more and more sides. Because the more sides you can encase the circle in, the closer you get to the arc of the circle. This argument gives us the value of pi, but Archimedes also used it to calculate the area of the circle. Now let's take the hexagon diagram. What he did was he calculated the area of the blue polygon, the blue hexagon, and the red hexagon, and he figured, okay, the circle has to be somewhere in between. So the calculation for this area of smaller hexagon is the side length, half the side length times this height, which is a little bit less than the radius. The calculation for the bigger triangle here is half of this longer side length times the radius. And if you imagine this piece of the pie, this arc of the circle, this sector of the circle is somewhere in between these two. So if you cut this circle into 6 slices, you get something that looks like this. If you cut the circle into 6 slices and then stack these smaller rectangles on top of each other, you get the area of a circle lies in between the area of the blue hexagon and the area of the red hexagon. The area of the circle is the radius times half of the perimeter, which is really the circumference. So let's take that and figure out how we got to pi r squared. Well, the radius times half the circumference is pi times the diameter, half of that. What's half of the diameter? It's really the radius. So the area of a circle is pi r squared. Taking a step back, this is by taking a circle and encasing it in and refining it into tinier and tinier, or rather polygons with more and more sides that more closely approximate the arc of the circle. And in this way, this process of slicing and then adding up gets you something that's closer and closer to the area of the circle. He used the same argument of slicing shapes and then calculating their areas to calculate the surface area and the volumes of a sphere. As with areas of shapes, it's only possible to calculate surface areas and volumes of spheres or of shapes that have flat sides and straight edges. Problem is, spheres are round. And so the closest thing you can do to calculate anything with something so round is by comparing it to something that's a little bit round and a little bit straight, like a cylinder. Here we'll talk about how he calculated the surface area of a sphere. What he did was he took a horizontal slice across the sphere and he calculated the ribbon that would be the portion of the sphere, and then the ribbon that's the portion of the cylinder. The portion of the sphere is colored here in blue. The portion of the cylinder is colored in red. And you'll notice that the blue ribbon is a bit narrower, but it's slanted at the edges, whereas the red is a little bit longer and straight at the edges. And he calculated that these two areas are actually very, very close to each other. The finer you slice the cylinder and the sphere, the closer those are together. And if you can, if these two areas are the same at this slice, and they're the same at this slice, and they're the same at any way you slice the sphere, they're actually the surface area of the sphere is actually equal to the lateral, the rounded surface area of the cylinder. So the way you calculate, the only thing you have to do to calculate the surface area of the sphere is to calculate the cylinder. And how do you do that? Well, imagine you have a piece of paper that's curved all around. Well, what you do is you could slice it and then uncurl it. So imagine this cylinder being uncurled. The height of this and you form a rectangle. Height of this rectangle is the same as the height of the cylinder, 2r. And the width of the rectangle is the circumference of the cylinder, which is pi times the diameter, 2 times pi times r. So the surface area of the cylinder is 4 times pi times r, base times height. Now that pi r squared, we saw that before. That's actually that actually stood out because this is the area of just the circular cross section of the sphere. So when Archimedes wrote about the surface area of this sphere, he didn't call it 4 pi r squared. He called it 4 times the area of the great circle. The great circle being the circular cross section of the sphere. Next, Archimedes calculated the volume of a sphere using a similar diagram in the same cross sections. What he noticed was that when you take a slice, let's call it a very thin slice of this shape, what you get is a donut hole on the left. And the cross-sectional area of that donut hole, or the annulus is the proper name, is actually the same as the cross-sectional area of a cone that's oriented just like this. Here's a top view of what that might look like. as you if you calculate if you draw the shape for different cross sections going up and down the sphere on the left, the sphere and cylinder on the left, the white part in the middle is the space occupied by the sphere. The outer edge of the red ring is the area occupied by, or the surface occupied by the cylinder. And so the space that's left over is highlighted here in red. That at that same cross section, if you look at the cone, it has this blue area. And these two are actually the same. Archimedes justified this using some things you knew about triangles and how the shapes are oriented when you take a horizontal slice across the cone and the sphere and the cylinder. So because the horizontal cross sections have the same area, you can actually you actually know that the gap between the sphere and this and the cylinder is the same as the volume of the cones. Well, one thing Archimedes knew about cones and pyramids was that the volume of a cone is 1/3 of the area of the base times the height. So the volume of these two cones combined is actually 1/3 of the volume of the cylinder. Well, if the sphere is everything that's left over after you take out the cone, the volume of the sphere is actually 2/3 the volume of the cylinder that's left over. And that's where we get the formula 4/3 pi r cubed for the volume of the sphere, simply by comparing the shapes that you get when you take the sphere out of the cylinder. As a quick recap, Archimedes was able to calculate the area of his circle by comparing it to polygons that got closer and closer to the edge of the circle, the more sides you use in the polygon. The surface area of a sphere is due to taking horizontal slices and comparing the surface area of each slice of the sphere and the cylinder. And he calculated it as 4 times the area of the great circle of the sphere. Last, he calculated the volume of a sphere as being 2/3 the volume of the cylinder that encased the sphere. It still leaves me one. This was thinking about this still left me wondering what's so special about this diagram that Archimedes really wanted to be remembered by this. Well, to me, the thing that's special that is worth celebrating here is Archimedes came up with a new way to think about geometry problems. He didn't calculate things exactly. Well, he calculated things exactly, but he wasn't able to calculate things about spheres and circles exactly because they're round. He did so by using continually refined approximations, by slicing up these more complicated looking shapes into smaller and smaller pieces and then adding them up. That's a baseline of a lot of modern math. There's an area of math called calculus that does this exactly. And he did this about 2,000 years before people in the modern age were able to do this using different tools. I think math tells us something a little bit more special about humanity. And I think that's another thing Archimedes probably wanted to be remembered by. Math gives us the ability to understand the natural world around us. It gives us math along with ingenuity, allows us to solve problems that we would otherwise think are impossible. Math makes it even possible to do things we don't even think could ever happen. Even so, the formula pi r squared is something we might take for granted. It's something that we're kind of given as a known. And I think that's okay. I think it's good to know these things and have these facts in our back pockets. But if there's anything I'd like for you to leave this presentation with, it's knowing that pi r squared wasn't easy. Why? Because pi's are round. Thank you.